Welcome to another edition of Math That Matters. This will be lecture LA-5, Logic and Argumentation 5. Today we're going to look at valid and invalid arguments, but not informally. We've already kind of looked at what makes an argument valid or invalid in an informal kind of verbal sense. But now what we're going to do is we're going to learn how to test the symbols and not just our intuition. So as always, I think you're going to love it because this is super fun. But let me share my screen. Always hard to talk and do something else at the same time, like chew gum and walk, things like that. But I have some deficiencies. Look at what I've just done. It's terrible. Here we go. I promise you, within moments, great things are going to happen. And they're happening. There it is, valid and invalid arguments. So what I've done here is I've actually taken some information from the logic book in sections 2.6 and 2.11, and then a few problems from the discrete math book and just kind of lumped them together. You'll get to do some proofs today using logical equivalencies, a little bit from the last video. Then you get to do some proofs, validations of arguments using Geesh, what's going on? It's been a long day. It's been a long day, and probably this isn't the time you want to do a video, but I'm doing it anyway because I got grit, right? That's what I want. Now I'm going to push through. So using truth tables to show that an argument is valid or not. So there'll be a worksheet with this, and you'll see that on Foxtail. All right, a couple of pieces of information that are review. An argument is a sequence of statements aimed at demonstrating the truth of an assertion or conclusion. And so the last statement, it's sort of therefore the last thing is your conclusion, but all the statements before it are premises that hopefully are connected together well enough that you can say they actually form a train into having to decide that the conclusion is valid. So hopefully they're true, but what we'll be testing today is, do they fit together well enough? Is this a puzzle that's done well, or did you just take some of the pieces and you're like, I'm going to make these things work, and you just kind of jam them together, even though the puzzle pieces don't fit. I used to do that when I was a kid. It doesn't work that well, but you know, you feel good about your work. Not really though. All right, you might want to take a picture of this slide because we are running into, I don't know if it's symbol heaven or the other place, but we're going to start saying things a lot with these different symbols. So when you see the upside down capital A, that means for all, that's a universal statement. The capital E that's backwards is the existential statement, or there exists. Depending on the book, you get different symbols, but such that is either this like vertical bar or kind of a backwards epsilon sort of looking thing. Conjunction is our and. Typically we have this symbol, this kind of hat caret thing, but sometimes they use a little dot and they mean and. That's kind of annoying, but whatever. Or is the V, the big V. Also implies we're used to seeing the arrow, but our logic book uses what they call this horseshoe thing, which also is annoying because I like the arrow better, but I like the tilde and I don't like this little L thing for the negation. So you just have to keep going back to this chart until you have these things memorized, but you really should memorize them. For contradiction, some books use like a kind of an emboldened lowercase c, but others use this kind of asterisk looking thing. Suppose is a capital S with a little line through the bottom. This is the closest character that I could find to suppose. And of course, you can use the words, but you're not going to see them in words. You're going to see the symbols. 3 dots in a triangle means therefore. So make sure that you're getting familiar with these symbols, because if you can read and know them instead of having to go back and look, it just makes it so much easier. But you're going to have to commit some things to memory so that you can be fluent in this new language, this symbolic language of logic. All right, so what we're going to try to do is we're going to try to take statements, and some of them will be atomic, just these really simple basic statements, and others will be molecular, whereby they're put together with ands and ors and ifs and thens. So this is what we'll be doing. If Jane is a math major, or if Jane is a computer science major, then Jane will take Math 150. Jane is a computer science major. Therefore, Jane will take Math 150. Hopefully by intuition, you can kind of look at this and say, I think that works. I think that's valid. Those things are well put together. How are we going to do this? We're going to make an assignment. So we're going to say, let's just say Jane is a math major, and C is Jane is a computer science major, and G is the statement math 150. The argument then in symbols would be, when we see this arrow, we read this as an if-then statement. So it would be if Jane is a math major or Jane is a computer science major, then Jane will take math 150. That's the first premise. The second premise would be Jane is a computer science major. Therefore, the conclusion is G, Jane will take math 150. And it turns out this is a valid argument. And you can kind of get the intuition here. M or C is true if one or the other is true. And so the if part is met of the statement. And if the statement is true, the then part must follow. And so we see that because we've satisfied the if part, and the then must follow. I feel like I'm going to sneeze right now, which is not the best thing to do when you're on a video and you don't have the skill to push pause because you think you'll mess something up. But I'm trying to work through not sneezing. Although, hold on. Nope, false alarm. Sorry about that. You know, I just have I don't know. It's, nope. You've been here with me. You're feeling my pain right now. All right, let's continue on. All right, so we're going to be given some words, and hopefully we can turn these words into symbols and then eventually test those symbols. But I think that this slide is helpful because here's argument 1, and it's about computer stuff. And here's argument 2, which is real mathy. And they look totally different, but they're actually the exact same argument. So I'll read them to you, and then I'll show you the form of the argument. So what we can do is we can look at an argument of this form, and we can test it. And then if it passes the test for validity, we can say it's valid. What's valid? Argument number 1 and argument number 2 are valid because they're really not different arguments, even though they look totally different. So here it is. If the program syntax is faulty, or you start looking for words like or, words like if and then, things like that. Or if program execution results in division by 0, then the computer will generate an error message. So you see we have an if-then statement. So if you were going to translate that, you've got an arrow, but there's also an or in the first part. Therefore, there's our 3 dots right there. If, so the conclusion is actually another conditional statement, an if-then. Therefore, if the computer does not generate an error message, that's kind of interesting. It was talking about a computer generating an error message, and now it's talking about, in the if part, the negation of the previous then. So I'm starting to think about like a contrapositive kind of thing, because I'm turning a then to an if, and I'm negating it. So what you're doing is you're reading something, but while you're reading, you're interpreting and you're translating. And eventually we're going to put this into symbols. So the then part is then the program syntax is correct. And, oh, there's an and. So we've got an and. That's actually kind of interesting too, because I remember when I negate some sort of or statement, I actually get an and statement with negations. That was De Morgan's law. So remember, you kind of have to have some of these principles and equivalencies and symbols right at the front of your brain, not the back of your brain, so that you can begin to translate into logical arguments. So, and then look at, it says does not result in division by 0. So we see some things here that give us an indication that we're doing some negations. There's an or up here that appears to be getting negated down here because there's an and statement, and there are some nots. Well, it's interesting because argument number 1 is exactly the same in terms of its structure as argument number 2. Here it is. If x is a real number such that x is less than -2 or x is greater than 2, then x squared is greater than 4. Therefore, see, there's a matching therefore, and there's another if-then statement. But it says if x squared is not greater than 4, wait a second, that looks like the opposite of this. So I'm thinking contrapositive again. Then x is not, I see a not, I see an and where I saw an or earlier, kind of what the negation of an or is an and statement, but it's the and of the nots. And look, there are the nots. So how in the world do you take something like that, which seems to be twisting your head into pretzels, and represent it symbolically and show that actually these two arguments are exactly the same in structure? And eventually, how will we be able to test those and see if they're valid or not? But first of all, we'll just show that they're the same. So look at this. What's in yellow here is exactly the argument form for both argument number 1 and argument 2. And all it is if P or Q, if the program syntax is faulty or program execution results in division by 0, so there's P, syntax is faulty, there's Q, division by 0. If P or Q, then R, something else. What is it? Computer will generate an error message. I call that R. Therefore, so there's our 3 dots. Therefore, if not R, if the computer does not generate an error message. Look, I don't want to use more letters than I need to, and I already talked about generating an error message being R. So if not R, then the syntax is correct. So that'd be the opposite of faulty, right? And program execution does not result in division by 0. So that's the opposite of division by 0. So if P or Q, then R. Therefore, if not R, then not P and not Q. And in fact, that is really just, the second part is really just the contrapositive of the first part, which we know to be equivalent to the first. And that yellow argument form is exactly the same thing for argument 2. You can look through it and check it yourself as argument 1. So those are the same arguments symbolically and structurally speaking, which I think is really interesting and really useful, because then we can just take particular structures and we can say, this is a correct structure, this is a valid structure, and you don't have to go back and do all the work to reprove certain types of arguments. You can name them, you can prove them, and then you can use them. As we mentioned before, an argument is not a dispute, it's a sequence of statements that ends in a conclusion. And we're going to learn how to decide if the argument is valid or not, whether the conclusion has to follow from the preceding statements, the premises. So we'll be looking at the form of the argument, not necessarily the content today. And as mentioned before, the first statements before the final statement are called the premises, and the final statement is the conclusion. The argument will be considered valid if and only if, that's a biconditional statement in and of itself, whenever statements are substituted in that make all of the premises true, the conclusion is also true. So what you get to do is you get to look for true premises and see if they lead to a true conclusion. So we want to make sure that the form is solid before we decide, yeah, we can use that. And of course, once the form is solid, that doesn't make the argument necessarily sound or true, because all of the premises have to be true in order for the argument to be sound. But if the premises are true and the conclusion has to follow, that means we have a valid argument. All right, so here's an argument, and we're going to have to try to decide, is this good? Is it a valid argument? Here we say, there's arrows, so we're going to read if then. So if P, then Q or not R. Second premise, there's an arrow. If Q, then P and R. Conclusion, therefore if P, then R. So that's how you would read that in words. So let's think about this. What does this mean? This means that P could lead to Q, but it also could lead to R. And we have an or here, so we have an option. P could go to Q or it could go to not R, but it doesn't have to go to both because our operator is an or. Q goes, well, that's interesting. Q goes back to P and Q also goes to R. Does that mean that P has to go to R? So you can pause the video if you want to and think about that. Does P have to end up at R? Now, one of the things you could do is you could substitute meanings in for the statements P and Q and R, and then kind of think through, does this work or not? Another thing that I like to do is I like to draw a little diagram and say, does this conclusion have to be true? Does P have to end up going to R based on these two premises? And watch this. So I made this little diagram. First premise says P goes to Q or not R. So I wrote P and I have P going to Q, but P could go to not R. There's another option. P doesn't have to go to both. It could go to Q or it could go to not R. Premise 2 is that Q goes to P. It actually goes back to P. And Q also goes to R. So Q is going back to P and Q is going to R. And therefore, the conclusion is that P has to go to R. But I think you can see here that P could go to Q and then wrap back to itself. P could go, P also actually, there's an and. So P has to go that way and wrap back to itself. P also has to wrap over to R because we have an and on this statement. But what we don't see is that P is forced to go to R because P could just go to not R. And that's because we have an or in the first statement and not R is an option. Q isn't forced upon us because of this or. So that might help the intuition, making a little diagram, a little tree diagram. Actually, this is not a tree diagram, technically speaking, in graph theory, because this is a circuit and trees don't have circuits, but you don't care about that. Here's how you test that. Like if this intuition is just not working for you, what you can do is you can go and you can put all of these into a truth table, which we learned how to construct last time, but we're going to use the truth table for something different. So I'm going to make sure that when I make my truth table, I include, well, I've got P, I've got Q, and I've got R. So I've got 3 different atomic statements. I'm going to include those in my truth table, as well as the knots of those things. And then I have to make sure that my premises end up being column headings in my truth table. Let me show you what I mean. So this is kind of crazy. This is a lot of work. But because we have 3 atomic statements, P, Q, and R, and because I have to look at all the possible truth values for P, Q, and R, whereas like all of them could be true, or down here, you see all of them could be false, or any combination of falses and trues that P, Q, and R could take. So since I have 3 atomic statements, there's going to have to be 2 to the third, which is 8 rows, to make sure that I consider all possible things that could happen with P, Q, and R. Now, these columns in this truth table are sort of accessory columns that are going to help us decide whether there are true or false values in the premises and in the conclusion. You can make as many auxiliary columns as you need, but since we're going to be talking about not R over here, the person that made this had a column of not R's, but not R is just the opposite of R. So whatever R is, you see not R is the opposite. If this is true, this is false. This is false, this is true. Notice there's an auxiliary column here that's Q or not R because Q or not R is a part of this premise right here. So the author of this truth table thought it would be helpful to have Q or not R because I'm going to want to know whether that's true or false down the road. Also, you see an auxiliary column P and R, and that's because P and R shows up over here later. And I'm going to want to know if P and R is true or false. So you can see the construction of this takes a lot of work. Now, you have to make sure that your premises and your conclusion are column headings in a truth table if you're going to test this argument for validity. And then what you have to do is you have to say, well, the same rules as the last lecture on truths and falsities. So if I have something like this and I'm wondering, is this true or false? I would say the only time a conditional and if-then statement is false is when this part is true, but this part is false. So I'm looking for where P is true, but Q or not R is false. Where P is true, but Q or not R is false. Right here, where P is true, but Q or not R is false. And actually, that's the only time. So you see, this is the only false in this whole entire column because all of the other situations are either directly true or vacuously true. And remember, vacuous truth is wherever P is false, if you go over here, wherever P is false, automatically that conditional that has P in the if is labeled true. So all these are vacuous truths. This second premise of the argument, if Q, then P and R, I'm looking for where this is false. This is false where Q is true, but P and R is false. Where is Q true, but P and R is false? It'd be right there. See, Q is true, but P and R is false. Therefore, this is false. And down here, you see in these two instances, false, false, we have a true Q, but a false P and R. So these would be false, and all the others would be true. Finally, our conclusion, P implies R, we have to decide, when is this false? Well, this is false. P implies R is false when P is true, but R is false. That's the only time this is false. And you can see that P is true and R is false right here. P is true and R is false, which means that statement is not true right here. Now, what we want to do with this truth table is different from what we wanted to do when we were showing logical equivalencies. What we're doing here is we're testing an argument for validity. So this truth table has a different function than showing logical equivalencies. What we want to do is we want to look at only the rows where the premises are true, and those are called critical rows. So these two premises are true here and here and here and here. All of the other rows that don't have blue highlights are not critical rows, and we don't have to worry about them. However, an argument is valid when in every critical row, the conclusion is true. And what you see here is that in this critical row, the conclusion is true. And in these two critical rows, the conclusion is true. But in this particular critical row, the conclusion is false, which means there is a scenario where the premises are true, but the conclusion is false. There is a scenario where P doesn't end up going to R. And because of that, this is not a valid argument form. For an argument to have a valid argument form, all critical rows in the truth table need to have true in the conclusion. That's kind of tricky. We're going to practice some more. Excuse me. All right. That's what I just said verbally. All right, now we've got some valid argument forms, some of which we will demonstrate their validity with a truth table, and some of which we will just use later on, because at some point you prove these things and you say, this works. Doesn't my throat know that I'm making a video? This doesn't quite seem fair, does it? Maybe it's not the water that clears your throat. Maybe it's the coffee. Doesn't it seem like coffee is better than water? And coffee and Jesus are two of the greatest things on the whole world. And my wife and my kids and Neil. Now that I've drank some coffee, my throat ought to be fine. All right, so there's these funny names for these different argument forms that are valid. And we will, like I said, demonstrate their validity with a truth table. You can do it with all of them, and you'll have to do some of them in your homework. But let's just kind of talk through them and get the intuition of why these are valid. I mean, I think most of these you're going to say, yeah, that makes sense. And then we will demonstrate their truthfulness. All right, so modus ponens in Latin is the method of affirming. And this is pretty straightforward. It says, if P, then Q. P, therefore Q. Like, duh, right? This just says Q follows P. If that's a true statement and I have P, I get Q. If you drink coffee, you will stay awake. Not working that good for me today because I was actually up from probably 3 to 5 this morning, and that's kind of painful. So, well, maybe I drank coffee yesterday, lots of it, and maybe that's why I stayed awake. So if you drink coffee, you'll stay awake. You drink coffee, therefore you stay awake. All right, modus tollens is, in Latin, the method of denying, simply says, if P then Q, not Q, therefore not P. That should be really familiar to you because that essentially is making use of the contrapositive as a logical equivalent. So for free, we know the contrapositive of if P then Q is if not Q, then not P. So this is like similar to modus ponens. Here we go. Here's an example. If a person is a sinner, then God will not listen to them. This is from John 10, and we just talked about that in the last lesson. So this is the guy that was blind, right? Yeah, the guy that was blind that Jesus healed. And so the guy uses these words against the Pharisees, and he says, but wait, God listened to Jesus. You know, he gave healing. He listened to Jesus. Therefore, Jesus must not be a sinner, right? Because if what you said was true, then I can come to this conclusion. And of course, he didn't say, and by the way, I'm using modus tollens, but he should have. That'd be great if that was in scripture. You can tell that I'm tired because I start getting a little silly and a little foolish, but that's okay. I just need some grace from you. Chapter 5, for more than a carpenter, used modus ponens, and lots of you made mention of this as this is a really strong argument. It's a valid argument form, and it just seems like the premises are true. If objective moral values exist, then God must exist. Objective moral values exist, therefore God must exist. Like, I mean, it's pretty difficult to say that moral values don't exist. And then you say, well, where did they come from? They must have an origin. That origin maybe is called God. And so we come to that conclusion. It's very difficult to deny these things. Even these premises just seem true. And certainly the modus ponens argument form is valid. So that was convincing. Look at all of these. My goodness. These have strong intuition, and we can prove them using a truth table. So I won't give an example of each. I'll give examples of some of them, but this should make sense. So if you say P, therefore P or Q, this is called an addition argument form, because if P is true, P or Q is true because P is true, and P or Q only requires one of the two things or of the many. So you can add Q if you want to an or statement, and if the first part's true, then you can add as many things as you want, and the whole statement is true. Conjunction, P is true, Q is true, therefore P and Q is true. Not that interesting. P and Q, therefore P. Of course, right? Because P and Q means both are true, therefore of course P is true. You can do the same thing with Q. Starts getting more interesting here. P or Q, not Q. Therefore P, right? If P or Q has to be true, but you know that Q isn't, then the other thing has to be true, as long as P or Q is true. Or transitivity, which one of our books calls the hypothetical syllogism. If P, then Q. If Q, then R. Therefore, if P, then R. That makes sense. P goes to Q, Q goes to R. That means P gets to R. This one is division into cases. P or Q, P goes to R, Q goes to R, therefore R. Right? If this is true, P or Q, and both of the things in the or end up at R, you got to end up at R. Here's another one that all mathematicians love, unless they're snobbish, because some mathematicians won't prove this way, but most of us do. How about this? Not P implies a contradiction. In other words, if not P, then you get something untrue. Therefore, the opposite must be true, P. We're going to look at that one. That's great. I love that. And finally, our logic book gives us this one more. And there's lots of other valid argument forms that are named, but these are all the ones that we sort of have with us right now. So here it is, constructive dilemma. P or Q. P goes to R, Q goes to S. Therefore, R or S. That's kind of interesting. It's a little bit more complex. And so I have an example from the book for that. Here it is. It's kind of a scary one. The killer is either in the attic or the basement. If the killer is in the attic, then he is above me. If the killer is in the basement, then he is below me. Therefore, the killer is either, you fill in the blank. Now, wouldn't it be above me or below me? That's called the constructive dilemma. All right, how about this one? This one you've used lots of times. This is how we string things together. I don't know if most often, but maybe most often. If P, then Q. If Q, then R. Therefore, if P, then R. How would we actually prove that? How would we demonstrate that this is a valid argument form? Not just with intuition, not just with an example, but with a truth table. So that means we have to take and we have to get into this truth table. P implies Q, that's premise 1. Q implies R is premise 2. And P implies R is the conclusion. That means we've got 3 atomic statements. We've got P, Q, and R, which means we need how many rows? You guessed it. We need 8 rows. 8 rows because we have to consider all the possible true false values for P, Q, and R. So I usually just do true, 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 false, true, false, true. So I'm doing 2 trues and a false. And then here's 2 falses and a true, true falses and a true, 2 falses and a true. 2 and true are too close. So you work your way from all trues to all falses, considering all possibilities. And I probably don't need to continue reminding you that P implies Q is only false when P is true, but Q is false. So I'm just looking for where P is true, but Q is false. P is true, but Q is false. In these 2 instances only, therefore, I have falses here, and all the rest are trues, whether they're vacuously true because P is false, or directly true because P is true and Q is true. Same idea for Q goes to R. I look at Q, I say, where is Q true and R false? Q is true and R is false here. Q is true and R is false here. And all other instances, Q goes to R is true. Finally, I look at P and R, and I'm looking for where P is true and R is false. P is true and R is false here. P is true and R is false here. That seems like a lot of work. It is. You can pause the video. You can make one of these yourself if you want to. But finally, I'm looking for only critical rows. That is where the premises are true. Premises are true here. Need more coffee. Premises are true here. Premises are true here. Premises are true here. And look, where the premises are true, the conclusion is always true. That means this is a valid argument form, and we can now say that we have proved the transitivity, which is the syllogism. Sorry, some books call it transitivity. I'm so used to that, but it is a syllogism. All right, so I tried to incorporate some logic used by Jesus or other biblical authors or characters. So I'm just going to take a little pause in the middle of all of this because I think maybe you get a little bogged down by the P's and Q's and all of the symbols, even though that's fun too. The Bible is even better, right? Jesus is proving his identity. And by the way, elsewhere in John, he says, if you do not believe that I am who I say I am, then you will die in your sins. So we see that Jesus is talking with people and he says, I've proven, the proof of who I am is revealed by all the miracles that I do in the name of my Father. So I love that because Jesus is even talking about how he wants to demonstrate without, without a reasonable doubt who he is, that we might come to believe. I thought this was another interesting statement. This was from John 10. Here's this statement. Jesus actually puts a conditional as the if in another conditional that ends with an and statement. So Jesus is obviously, he is the Logos, right? He is the Word made flesh. And so the Logos is using brilliant logic and complex logic. He says here, if you see me doing the beautiful works of God upon the earth, so if you see me, using the beautiful, doing the beautiful works of God on the earth, then you should at least believe in the evidence of the miracles, even if you don't believe my words. So there's an if then, but then he's got a then. So the if then is actually the if of another if then statement. Then you would come to experience me and be convinced that I am in the Father and the Father is in me. Then you would come to experience and be convinced that I am in the Father and the Father is in me, which is really interesting because in mathematics, when we're trying to show set equality, we show that one set is inside of the other and that the other is inside of the one. And so Jesus is claiming equality with the Father here. And of course, they understand that because the Pharisees and the teachers of law are smart too. And so they accuse him of blasphemy. See this in John 10:33. They say, we're not stoning you for any good work, but for blasphemy, because you who are a man declare yourself to be God. They understood what Jesus was saying here. They understood his logic. So let's see, is this a valid or an invalid argument? We could test this with the truth table. So here's the first premise. If you are a man and you declare yourself to be God, then you have committed blasphemy. So here's my first premise in symbols. If you're a man and you declare yourself to be God, then you've committed blasphemy. And then they're like, well, Jesus is a man. Jesus declared himself to be God, right? So man and God is true. Therefore, Jesus committed blasphemy. So by the way, before we look at the validation of this argument, because it is a valid argument form, consider this. What would or wouldn't make this argument sound? Remember, there's a difference. Valid just means the structure is good. So they're validly arguing that Jesus has committed blasphemy. And so we would have to come back and to say that Jesus has not committed blasphemy, we would have to say that this argument, though valid, isn't sound, right? And so soundness means that all of the premises are true. So somehow we would have to say either this isn't true. If you are a man and you declare yourself to be God, then you have committed blasphemy. We would have to say that that isn't true, or that Jesus isn't a man, or that Jesus didn't declare himself to be God. Maybe Jesus is more than a man. So that's how we would have to look at this, because it ends up that it is a valid argument form. And here it is. So premise one is right here. If you're a man and you claim to be God, then you've committed blasphemy. But I couldn't put the truth values in for that until I had created my 3 atomic statement columns. So this is man, this is God, this is blasphemy. Again, there's 3 statements, so I had to make 8 rows looking at all the truth values for these 3 things. I don't really need these 3 columns because I'm not using any of them over here, no negations over here. But I do have an if part over here that's a man and God. So I made another man and God column. That means that man and God is true when both man and God is true. So true gives me a true over here. And you see down here, there's a true also there because we do have man and God being true there. However, premise 1 is only false where man and God is true, but B is false. Man and God is true, but B is false right here. Man and God is true, but B is false right there. So this is the only false in that last column. Obviously, knowing how to decide on a truth value for an if-then statement is really important. We just do it over and over again. If you don't understand how to do that, come and see me. I'll help you with it. But note, premise 1 is right here. Premise 1 is, I'm stuck. There we go. Premise 1 is right here. And premise 2 and premise 3 are here. This is the only row where premise 1, premise 2, and premise 3 are true. And in that row, which is the only critical row, the conclusion is true. Therefore, because this critical row has true premises and a true conclusion, we can say that's a valid argument form. All right. A little bit more. Let's keep going for a bit. The contradiction rule is very, very widely used in mathematics, and I think probably not enough in like debate. So the contradiction rule is not P leads to a contradiction. In other words, if not P, then something counter to reality happens. Something happens that's always false when not P is assumed. Therefore, P is true. So what we do with proof by contradiction, it's a technique. So we're trying to prove something and we just say, hypothetically, let's pretend that the opposite is true. And let's see what the implications are of assuming the opposite. And in fact, if I can get the implications to lead me into a contradiction, and in math, it's kind of like a contradiction where you say, this number is odd, but it has to be even. And you say, well, that can't be, or this number is negative, but it has to be positive. So you get to a contradiction where you say, I assumed the opposite, and that was a bad assumption. So the opposite of the opposite must be true, which is the thing I was trying to prove. I also think this is an excellent tactic in debate. It doesn't happen often enough where you kind of look at your opponent and you say, okay, you can have it. You're asserting something. Let's just pretend, let's suspend my contest, suspend my debate, suspend my pushing back. Just suppose that you're right. Suppose that what you're asserting is true. And let's just see if we can live with all of the implications of that. And pretty soon you say, look, you've run into a problem, haven't you? You've run into either something that has to be true and is a contradiction, or even if it's an inductive argument, you could say you've run into something that's so unlikely that you might have to reconsider because you have to live with all of these other things because where your position implies such and such. Now, you have to be careful with this in that unless your opponent truly is asserting the opposite of your position, you might commit the fallacy of what's called a false dichotomy, because if your position isn't exactly opposite of theirs, there may be a third position. There isn't always just two positions. So you have to be careful with that. And we'll talk about fallacies later. All right. We love proofs. We love showing that we have valid argument forms. And I'll show you two ways, using logic laws and then a truth table. Ultimately, you especially need to be able to make a truth table, although we do use some logic laws to do some proofs, two proofs in the homework, so that's fun too. So how would I prove that the contradiction rule is a valid argument form using logic laws? This is going back to this table of logic laws, which we talked about in the last video. So here's what I would do. Here's my argument. Premise one is P or not P. That's just a tautology. It's called the negation law, like something or the opposite of something. That's always true. It's a tautology. Premise two is if not P, then contradiction. Now you might remember from the last video, we can actually change an if then to an or statement for free because we have this equivalency. We know that P implies Q is the same thing as saying not P or Q, which is really useful. Because if P implies Q, I can say not P is true or P, of course, but P goes to Q. So that's kind of helpful because I can change this into the opposite of the if or. So I can say P or not P, but not P goes to a contradiction. So I'm changing this to, excuse me, I'm changing this to an or statement using this logical equivalency. Therefore P, so I have not P or a contradiction, but a contradiction is always false, but this is an or statement. And so P must be true, which is, I think, a strong argument for the contradiction rule being valid to use in an argument. But if you don't like that, this is probably the way you might do it. So basically premise one is P or not P. Premise two is not P leads to a contradiction, therefore P must be true. And the nice thing is this really just has two rows because we have one atomic statement. So we can say P could be true or false, which would mean not P is false or true. A contradiction is always false. P or not P is always true. It's a tautology. So this is a pretty easy truth table to fill in. But this one's important. Not P implies contradiction. This is an if-then statement. And so this is actually true wherever not P is false. And you see not P is false right here, which makes this statement actually true where not P is false. And it's false right here because not P is actually true, but the conclusion is false. So this is the only instance where that conditional is false. And of course, the conclusion is P. I've actually just rewritten P over here because it's written here, but it's the conclusion. So look, here's our critical row where our premises are true. And in this red critical row, this isn't a critical row, you see, because there's a false here in this premise. In this critical row, we've got a conclusion that's true. So it's a valid argument form. It's the way that you prove an argument form is valid. All right, I'm going to do 2 quick examples because this is the last part of your homework, and there's 4 questions in your homework that look like this. So what they do is they give you 1, 2, 3, and I actually don't like this part at all. I really don't like some of the ways that the formatting is done, but they're going to give you rows 1, 2, 3, and then they're going to give you this therefore and then something, but that is actually exactly repeated down here. So what they're trying to do is they're trying to say that with these 3 premises, you can actually get to this conclusion, and then they're showing you how, but they're not giving you the reasons. So the things that are underlined in your homework are what you're going to have to fill in, but you're going to get for free all the rest of this stuff. So if you start looking through this, and they're using the horseshoe instead of the arrow, which is kind of terrible, but oh well. So this is an if-then statement. So they're saying if M, then not N. I'm sorry, if M, then not N. And then they write M is true. If H, then N. Therefore not H. Well, how do you get to not H? And the way you get to not H is by getting to not N. Well, how do you get to not N? They say modus ponens 1 and 2. Oh, wait a second. Look, if M, then not M. M is true. Therefore, of course, not N, because we've already got this statement that says not N follows M. But that's exactly what modus ponens says. If you satisfy the if part of the conditional, then you get the then part. So modus ponens allows us to have not N. And once we have not N, if we get this statement right here, the contrapositive of that is not N goes to H. You can turn it, goes to not H. So you can turn it around and negate it for free with the contrapositive, but the contrapositive is what modus tollens uses. So you can say not N leads to not H, but I have not N from modus ponens. So all you're doing is figuring out the name of the rule that lets you make this conclusion and which statements you put together when you use that rule. A little bit tricky, but not too bad. Let's do one more, and then we'll call it good for the day. All right, so here's an argument. A or B is true. If C, then D. If A, then C, not D. So you get all these things for free. These are all true. And you got to conclude that B is true. See, they've got B down here. But it's going to take a couple of steps to get to the B conclusion. Now, one of the things I noticed while walking through here is if you kind of rearrange this, remember, you get all these things for free. They're true for free. If A, then C, if C, then D. I'm like, wait a second, A routes to C and C routes to D. That means A routes to D. I know that. That's the syllogism. That's the transitivity. That means I can get that A goes to D, and that's what number 5 says. See, that's the syllogism, making use of 3 and 2. And I like how I put 3 first and then 2, because A routes to C and C routes to D. So you kind of use 3 first and then you use 2. Okay, fine. Now we've got A routing to D, but wait, we know for free we're given that not D is true. And that actually is the negation of the then part of this statement. So using modus tollens, I can turn this around and say not D goes to not A, right? The contrapositive of A goes to D is not D goes to not A, but I already know not D is true. So therefore not A must be true. So that's modus tollens using 5 and 4. And finally, I get B because look, I've gotten to not A, and therefore B must be true because I have up here that A or B is true. If A or B is true, but I know that A isn't true, then B has to be true in order for this statement to be true. And that's called the disjunctive syllogism. So it's a bit of work, but if you think through it, it can be kind of a fun little puzzle. All right, I've got a worksheet, LA-5. It's on the assignment calendar. It's on Foxtail. Hopefully you love it. And if you need help, come and see me. I think you might need help. So let's be careful with all of that. I don't want you to get a false sense of security looking at the answers in the back of the book because they're in the back of the logic book and some of them are in the back of the discrete math book. So be careful of that. Come and get help if you need it. Work together. Go to our math lab Sunday through Thursday, 5 to 9 p.m. in Lemons 15. They love this stuff. All right, friends, I will see you at the next lecture.